Okay, so Unit 4, chemical bonding. First off, types of chemical bonding. Well, actually, let's define it first, right? So bonding is the force of attraction that binds atoms together into compounds. Now, the reason why bonds exist is because elements are more stable when bonded. That is why it happens. If that wasn't the case, then you would just literally have piles of atoms outside everywhere, right? But the reality is, everywhere you go, you are surrounded by compounds. The atoms are all already bonded in some way, shape, or form. Right? And that is because that's how they exist. They are most stable when they exist. So we'll talk about the different types of bonds. We got ionic bonds, we have covalent bonds, which falls into two categories. Okay. So first we need to talk about this concept. Electronegativity. The definition of electronegativity is the ability of an atom to attract electrons in a bond. So electronegativity values are given to you here in this diagram, but they're also given to you on your periodic table. If you look at your periodic table, and you know you guys are going to need this out anyway, so it would be a good idea to take it out. Paper periodic table. The electronegativity values are on the bottom, right, of each period or each element box. So it's not something you ever paid attention to before when you were looking at this. But as you look at both the periodic table and this diagram here in the notes, you should take away from the fact that your electronegativity values increase from left to right. Right? So they are the highest on the far right side. And also, the electronegativity increases from bottom to top. Now, the trends are best represented when you only look at the S and P blocks. So I know they're showing you the D block here as well, but the trends get kind of messy in the D block and for lots of reasons that we're not going to go into. But if you just look at the S and the P, you clearly see the trends for electronegativity. This could have been a trend that we talked about last unit, but it actually is more relevant in this unit, so we kind of held off and decided to talk about it now. So, first and foremost, you should be able to find electronegativity for any element, right, on your periodic table. So, what's electronegativity for arsenic, As? 2.0, right? Okay. So, you're going to need to be able to do that. As far as why this trend is, if we look at the definition, if we're talking about an atom's ability to attract electrons, you already know something about that. The previous trends from the last unit, what are we talking about? The ability to attract electrons. We gave it a different name. Yeah, effective nuclear charge, right? Effective nuclear charge, when it gets higher, the protons attract electrons more. Well, that's what's happening here, right? Effective nuclear charge of boron is 3, of carbon is 4, nitrogen is 5, oxygen is 6, fluorine is 7. We left off the noble gases here because, as we discussed a number of times, the noble gases don't bond. So it's pointless to talk about electronegativities for noble gases. Okay. So, what do we use that value for? Now that we know what electronegativity is, how is it useful? We're going to use electronegativity to determine the bond type. You see, those values, whenever we look at elements and that are bonded to each other, we are going to take the electronegativity difference. And that is going to tell us what kind of bond it is. So when you take two elements, if their electronegativity difference is 1.7 or more, we classify that as an ionic bond. Okay, so an example of sodium and chlorine, okay? Those two elements. So if we look up the electronegativity of sodium, can you guys tell me what it is? Find it on your periodic table.
0.9.
Point what?
0.9.
0.9, yeah. So this is 0.9. And then when you look up chlorine, 3.0. Okay, so when you take the difference, you literally just subtract. So delta means difference. Delta En is equal to 3 minus 0.9. So we're talking about a difference of 2.1. And that's definitely greater than 1.7. And that's what we classify as an ionic bond. Okay. Then you have some combinations where your difference is 0. So if your difference is 0, like if you have two of the same element bonded to each other, right? Chlorine bonded to chlorine, well, that would be 3 minus 3. And so, of course, the delta En would be equal to 0. And so that bond is what we call a nonpolar covalent bond. But what if you have some difference, but it's not a huge difference? Like anything between 0 and 1.7, that's what we call a polar covalent bond. Okay, so first and foremost, I'm just going to add a page here, and I'm going to give you a couple of combinations, and I want you to be able to look up the electronegativities and then classify them. Okay? So, what if we had magnesium bonded to oxygen, phosphorus bonded to sulfur, and hydrogen bonded to nitrogen? Take a minute or two, look up those values, and tell me what kind of bonds would exist. All right, so for the first one, what do we have? Yeah, Caden.
Ionic.
That's ionic, yeah. 3.4 minus 1.2, it's going to be a difference of 2.3. Definitely ionic. What about phosphorus bonded to sulfur? Ojan?
Polar covalent bond.
Polar covalent, yep.
That's a 0.4.
Yeah, the D delta En equals 0.4. Okay, what about hydrogen bonded to nitrogen? Yeah, Mattia?
Polar covalent.
Also polar covalent. You can abbreviate just by PC. Delta En equals 0.9. Okay, pretty straightforward, I think, okay? Now, I will say that there are going to be some exceptions, and the reasons for those exceptions we'll talk about later on. But you can have ionic bonds with a smaller difference. Okay, that can happen. So Probably I won't show you anything like that right at the beginning, but later on we'll talk about why that might happen. Okay? So these are like suggestions. These rules will cover like 95% of the bond types accurately, but there's going to be scenarios where these rules don't necessarily work, and that's okay. On any quiz or any test, you're not going to be given any exceptions. You're going to be given pretty straightforward ones. Okay, so just make sure you know how to find them, how to calculate the difference. Okay, so let's talk a little bit more in depth about ionic bonding. So remember, ionic bonding is when you have a large electronegativity difference. The delta En is greater than 1.7. So if you looked at the periodic table and you had to pick two elements that would guarantee a difference of 1.7, how would you go about picking those two elements? Would you pick two elements that are like in the middle? Pick two on the left, two on the right? What do you think? Caden?
Two that are in the P and S block, but two that are far away from each other.
Far apart. You would pick two elements that are far apart, right? So one on the far left, one on the far right. Because you know electronegativity goes up from left to right. So what's the greatest chance of having the largest difference? Like alkali metals and halogens, for example. So if we review what we know about metals and nonmetals. Metals have low ionization energies. All right, we know this. All right, we know that metals produce positive ions because they don't hold on to electrons very strongly. They end up losing their electrons. We know that. Nonmetals have high ionization energies and high effective nuclear charges. It's difficult to remove electrons from them, and that's why nonmetals produce negative ions. So typically, and not all the time, but typically, ionic bonds are what results when you have a metal bond with a nonmetal. Okay? So what exactly is happening? And I'm going to add another page in here just so I could draw a little bit. Here's what happens. Remember how we picked sodium and chlorine in our first example? We identified this as ionic because we said sodium was 0.9, chlorine was 3.0, the delta En was 2.1. So here's what happens. The sodium atom has 3 energy levels. We know the sodium is 1s2, 2s2, 2p6, 3s1, and we know that this is the valence electron. Okay? Chlorine has 3 energy levels also. And it's 1s2, 2s2, 2p6, 3s2, 3p5. Okay? So there's this rule called the Octet Rule. And actually, it might even be on the next slide. Yeah, I'm jumping down here for a second, guys, then I'm going to jump back to that picture. There's this rule called the Octet Rule. And it states that when they form ions, atoms will gain or lose electrons until they have the electron configuration of the nearest noble gas. So however many valence electrons an element has, all elements are most stable when they have 8 valence electrons. That's why it's called an octet rule, right, for 8. So if we go back to our drawing here, sometimes this is clear if I draw a little orbital diagram. Here is sodium with its 1 valence electron. Here is, I didn't space these out right. Let me move this a little bit over. Here is chlorine. Chlorine has 7 valence electrons. What happens is, because chlorine has such a higher electronegativity, the electron gets ripped off from sodium by chlorine. And the result is you have a positive ion and you have a negative ion. Why was it able to take the electron away? It's because chlorine has a really, really high electronegativity. And once they form ions, they are now stable. Because now sodium has these guys here. These guys here. When sodium loses its valence electron, this becomes the new valence shell for sodium. And look, it's got a full octet. When chlorine gains an electron and puts it in here, now it has an octet. The goal is for each atom to have an octet of valence electrons. They're more stable this way. And sodium has a positive ion next to a negative ion. And that's that attraction right here that exists between these two. That is what we call the ionic bond. The attraction between ions. It even has the word ion in it. Okay, so that was kind of a lot. Let's condense this a little bit just to make it easier to digest. So what all is happening? In ionic bonding, we have a difference in electronegativity greater than 1.7. Electron is transferred to the more electronegative element. That means the nonmetal. And now ions form. Attraction results. So you can expect this kind of thing to happen anytime your electronegativity difference is 1.7, 1.8, 1.9, 2, 2.4, etc. As long as it's higher than 1.7, this is generally what happens. And as kind of a time saver, generally speaking, when you see a metal with a nonmetal, you can expect this, right? Most of the time. Oops. Usually a metal with a nonmetal. Okay, so are you guys clear on the concept of the octet rule? All atoms would like to have the same number of valence electrons as a noble gas. Some atoms give away electrons, like metals. Some atoms take electrons, like nonmetals. Let me give you another example. So if we have a compound like this, like magnesium chloride, for example, okay? Now, magnesium has 2 valence electrons. Chlorine has 7. But notice how there's 2 chlorines and 1 magnesium. So what happens is magnesium in the middle, electron is given to a chlorine on the left, and it's given to a chlorine on the right, because in doing so, chlorine then has a full octet. We'll make that electron red. And so does chlorine on the left. Now, when magnesium gives away its 3s2 electrons, it now has a full octet in energy level 2. So everybody has a full octet. And so the ions would look like this. That's a bad looking seal. Let me rewrite that. So you see how, like, even though the number of ions, it's not always going to be 1-to-1. It's going to be whatever it needs to be so that everybody gets an octet. In this case, magnesium gave 2 electrons away, but it didn't give both electrons to the same atom. It gave 1 to the left and 1 to the right. But it still worked out because everybody has 8. Okay, so that's ionic bonding. The electron is transferred, and then you have ions that are sitting next to each other that attract. So when ionic compounds form, they end up looking like this structure here. They alternate, right? You know that you can't have 2 of the same charge next to each other. You guys know that now. You know that would repel. So instead of having the same charges next to each other, they literally go negative, positive, and so that they're never next to each other. And that works out because now this way you have the maximum amount of attraction. This structure, by the way, is called a lattice, a crystal lattice. Okay, a crystal lattice is a repeating pattern, an organized repeating pattern. That's a lattice. Okay. So, if you looked at a grain of salt, like let's say you have a microscope at home, and you shook out some salt, and you put it on a little dish and looked at it through the microscope, you would literally see little cubes. They would look just like this. And if you crush some with your thumb, the big cubes would break apart, but guess what they would form? Tiny cubes. This is the way that the salt structure is arranged. And you could smush those down and zoom in even closer. You would still see little cubes. That's how they arrange themselves, right? And this pattern. Ionic compounds typically do this. So, what should you know about an ionic crystal? Well, you should know that each one of these is a positive, negative, and they alternate. You should know that there are attractions taking place between the opposite charges, which you know already. So ionic compounds are, and here's where we talk about properties, and this is going to be useful later. They're hard. Ionic compounds are hard. They are also brittle. Sometimes things that are hard also break and shatter, right? Like glass is hard, but glass can shatter, right? So glass is not ionic, by the way, but that was just, maybe that's a bad example. But they're brittle, and they have high melting points. What I mean by high melting point is if you took salt and you poured like a cup of salt into a frying pan at home, you could not melt it. You could turn the flame up as high as you want on your oven range, but you would not melt the salt because the temperature of that range just does not get hot enough to melt it. It would just stay there as, solid powdery salt. Right? You would need something that gets much hotter than that to melt it. So ionic crystals are non-conductors as solids, but they do conduct when they're in liquid. And let me explain that. All right, so here we go, adding another page. So in order to conduct, there's 2 criteria. So the particles have to be charged, and they must be mobile. Like they got to be able to move. So in an ionic solid, right? In an ionic solid, are they charged? Yes. Are they mobile? No. meaning they can't move. Those ions are stuck next to each other in place. They cannot move. They're fixed. But what if we melted it? So molten ionic solid. Are they charged? Yes. Can they move? Yes. If you were able to melt it, even though I said you can't do it on your oven range at home, but we have special burners in AP that get like twice the temperature of the Bunsen burners we have in this class, then we could melt salt. And we literally could take salt and make it look like a clear liquid. That's mobile. They're moving around because in the liquid phase they can move. So that is when it can conducts as a liquid. Okay, but not as a solid. Then there's also what we call dissolved ionic solids, or ionic. And what that means is, well, you know what salt water is, right? You guys, everybody has dissolved salt into water at some point. Once you dissolve salt into water, they break apart and you get ions in water and they can move. So yes, they are charged, and yes, they can move. So salt water conducts electricity. Okay. How can you tell if something is ionic? Well, look at its formula. Two ways. The quick way is to say, do you have a metal with a nonmetal? Oh yeah, then it's ionic. The other way to prove something's ionic is to calculate the electronegativity difference. Look them up and subtract. Okay. By the way, NO3 is what we call a polyatomic ion. So we have sodium, and we have a polyatomic ion. So when you see a compound with 3 elements, that means you typically have a polyatomic ion. But we'll be talking more about those later when we start talking about molecular shapes. Okay. We talked about the octet rule again. Gonna skip exceptions for now. Okay. You need to be able to predict the number or the charge on an element. And this is essentially based on how many valence electrons it has and what it needs to do to get 8 electrons around it. So sodium. Sodium has 1 valence electron. In order to have 8 valence electrons, sodium can do one of 2 things. It can either lose 1 or gain 7. Now we're talking about sodium, which is an alkali metal with a really low electronegativity. What do you think the likelihood is of sodium gaining 7 electrons? It can't even gain 1. So it's not gaining any electrons. So what's going to happen? It's going to lose its electron. So sodium's charge would be a +1 because it only has 1 electron to give. And you know what? The same is true for every element in this family. Lithium, cesium, rubidium, potassium, they all only have 1 valence electron. So that means the charge that they will have is +1 when they bond. Magnesium. How many valence electrons does magnesium have? Yeah. It has 2 valence electrons. Same story. It's got a low effective nuclear charge, a low electronegativity. It's a metal. If the choices would be to gain 6 or lose 2, it's not gaining 6 electrons. The only thing it can do is lose 2. So its charge would be +2 when it bonds. Calcium, same thing because it's in the same family. Barium, +2. So I'm not really keen on asking you to commit too many things to memory, but I will say that your life would be made easier and you'll be more efficient at working through these if you remember the alkali metals always carry a charge of +1 when they bond. And the second column, the earth metals, those guys are going to be +2. Okay? Which hopefully you guys can envision pretty quickly now since we spent all that time drawing out orbital diagrams. Okay, so nitrogen. How many valence electrons does nitrogen have? What numbered column is it in out of the tall 8 columns? Nick? Yeah, how many?
5.
It's got 5 valence electrons. So, the thing about nitrogen, there are its 5 valence electrons right there. So to have 8 valence electrons, it's either going to gain 3 or lose 5. Now, would you say that nitrogen has a high or low electronegativity? Relatively high. Things with high electronegativities, things with high effective nuclear charge don't lose electrons easily. So this element is not losing 5 electrons. So it's going to gain electrons. So how much space does it have? 3. So its charge will be -3. Are you guys understanding how I'm figuring this out? I'm looking at how many valence electrons it has, seeing what the likelihood it is of either gaining or losing electrons, and then seeing how many that would be to do that. So chlorine. How many valence electrons in chlorine? 7. Does chlorine have a high or low electronegativity? High. So its choices are either lose 7 or gain 1. It's not going to lose 7. It's going to gain 1. It's going to be a -1 charge. What about sulfur? How many valence electrons in sulfur? 6. So what's its charge? +6 or -2? -2. Do the next two on your own. See if we can come up with what charge would be. So what do we have for oxygen? -2 also. Oh, wait. That's in the same family as sulfur. That makes sense. Okay. Boron? +3. Yeah. Oh, what if you don't want to memorize what charges are? They're listed here. On your periodic table, on the backside where it says common valence charges. All right, so the first column is all metals. These are not all of the metals, but they're the most common metals. Okay, so one thing you should notice is that metals can only have a positive charge. It even gives you the hint in bold at the bottom. Right? And if you need to find the charge, look up here and find it. Now, some metals have more than one charge listed, and that's okay. There's reasons for that we'll get into later. The nonmetals. The nonmetals are your middle column. Right? So this is an important note here in bold. It says, whenever a nonmetal is bonded to a metal, the nonmetal's charge is negative. Okay, so if I said magnesium bonds to nitrogen, magnesium is a metal, so magnesium bonding with oxygen. Magnesium is a metal. Magnesium is an earth metal, so its charge is +2. Oxygen has 2 charges listed, -2, -1. The -2 is in bold because the -2 is what happens 98% of the time. You're basically never going to use -1 on your chart sheet for oxygen. You can even cross that off now, right, if you don't want to be confused by it. Oxygen is pretty much just -2. Okay. All right. We talked a lot about ionic bonding. But for this to make sense, we need to talk about the other types too. So, covalent bonding. When 2 nonmetals bond, they must share electrons. This is the key word, share. Share electrons. There was no sharing in ionic bonding. It was just taking. Covalent bonding, they're sharing. So what's happening? Why is it sharing? Well, let's look at hydrogen to begin with. Now, hydrogen, the orbital diagram is simply this. 1s1. In energy level 1, there is no p subshell. So there's no octet rule for period 1 elements. Okay, but having said that, hydrogen is stable with a duet. Two electrons. So how can a hydrogen atom have two electrons around it? Well, if it shares electrons with another hydrogen atom, right here. Each hydrogen brings its own electron, and when they meet up, they end up sharing a pair of electrons exactly in between them. And they're sharing the electrons equally. Some elements can share 2 pairs of electrons. Some elements can share 3 pairs of electrons. And we call those single bonds, double bonds, triple bonds, respectively. That will become important later, just kind of introducing that now. We're going to talk about bond length, bond strength later on. Okay, I'm going to skip that for now. Okay, so the third type is what we call, wait, you know what, back up, sorry. Did I talk about nonpolar covalent yet? Oh, no, there it is. Okay, so here. When electrons are not shared evenly, when your difference in electronegativity is between 0 and 1.7, this is what we call a polar covalent bond. All right, so let's say your difference is not quite 1.7. We did some examples where it was like 0.9 or 0.4. That is unequal sharing and not shared evenly. So if you look at this, hydrogen, chlorine, delta En is equal to 0.9. That's polar covalent, unequal sharing. Why is it unequal? Well, it's because chlorine has a stronger ability to attract electrons towards itself. So the electrons are pulled closer to chlorine than hydrogen. And when there's this imbalance of electrons, that's a polar covalent bond. Now, when this happens, we end up with partially negative and partially positive sides of a molecule. Okay? So this little figure here that you're looking at, it's called a delta, a lowercase delta. It looks like an eighth note with a charge written after it. Okay, that just indicates the different ends of a polar bond. Okay, so anytime your element's electronegativity difference is greater than 0 but less than 1.7, it's polar covalent. And the key term for polar covalent bond is unequal electron sharing. That's the most important aspect of polar covalent bonding, okay? Unequal electron sharing. So, let's say your dad gets a new car and he passes down his car to you and your brother is 2 years older than you. So technically, you and your brother are sharing that car, but let's be real. Who's really got the car most of the time? It's your older brother. That's unequal electron. Your older brother has greater electronegativity than you, okay? Okay, so then, in a non-polar covalent bond, your delta En equals 0. What does that mean? You have 2 elements with the same electronegativity. They're sharing equal. Let's say fluorine was bonded to fluorine. 4.0, 4.0, that's a 0 difference. When that happens, it's about as symmetrical as a molecule can get. There's no positive or negative side because everything is equal. And this happens with molecules that tend to bond to themselves. We call these diatomic molecules, and there's 7 of them. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. For short, just remember Hunkelbrief. That's how you know which ones are written with a subscript of 2. F2, Br2, Cl2, etc. Okay, so the key aspect of nonpolar covalent bonds, equal electron sharing. That is the key feature. It's a tug of war between two evenly matched opponents. Okay. So this slide here kind of sums this up nicely. 3 types of bonds. Let's go backwards because we talked about ionic first. In an ionic bond, it's an attraction between ions. Why does it happen? It's because the electron was completely pulled off of the metal. Positive ion next to a negative ion. That's an ionic bond. And that only happens when your delta En is greater than 1.7. Polar covalent bond. One atom pulls on the electrons more strongly than the other. That's why there's an imbalance of where the electrons are. Right? This is going to happen when you have some kind of electronegativity difference, 0 to 1.7. And then when you're exactly evenly matched, when the electronegativity is exactly the same on both elements, then it's equal electron sharing. And that's a nonpolar covalent bond. In case you're wondering why we're using the term polar, so the term polar means differently sided. So if something's polar, it has different sides. But if it's nonpolar, then it does not have different sides. Does that make sense? So, okay. How are we doing? Here's what you need to be able to understand. First and foremost, know what the term electronegativity means. Know how to use electronegativity to calculate bond type. So for whatever elements are involved, you just subtract. And then the number is going to fall into 3 categories, and that's how you identify what it is. You need to know the key features of each type of bond, right? So you need to know that nonpolar, the key feature is equal electron sharing. For polar, the key feature is unequal sharing. And then for ionic, you need to know that it's an electron is transferred. It's somewhere around here. Electron is transferred, and then you have 2 ions next to each other. Right? You need to know all this. You should be able to predict the charge on an element, what it's going to be. If I give you an element like phosphorus, P, what charge would it have when it bonds? -3. What's the reasoning? It's a nonmetal that will gain electrons, yes. It has 5 valence electrons. So in order to get 8, it's got to gain 3 more. Okay.